Okay, so let's continue with exercise 5.1.3. So this is going to be part 2. um, and so where I left off was I'm taking this propagator, U, applying it to the initial wave function, where I've expanded now the propagator out into terms according to a Taylor expansion, and I've also uh, expanded the initial wave function in terms of a Taylor series. And now, like the book suggests, now take it term by term. But what I'm going to do is something a little bit more elegant, and that is to actually just apply terms to the entire wave function as a series. But anyway, so the first thing we can note, though, is that when the first term here, 1, is applied to the wave function, then nothing changes. So basically, the n equals 0 term of the U expansion just returns the psi in its initial condition. Actually, that's not prime. It returns the psi in its initial condition. So the more interesting thing is now let's take a look at the derivatives. So before we do that, why don't we clean things up a little bit? And I'm going to say that alpha is I h bar t over m. And what that means is now for my propagator, I now have this expansion of 1 over n factorial alpha to the n power over 2 to the n power times the derivative 2n over dx 2n. All right, so I'm also going to get tired of carrying around this 1 over pi to the 1/4 power. So why don't I create a new shortened version of the initial wave function and call it psi pi of x 0 is 1/4, not 1/4, pi to the 1/4 power times the rest of it, that initial wave function x of 0. Anyway, I just wanted to, well, the 1 over pi to the 1/4, we'll just tack back in there. But it's just a factor that multiplies by all terms, so we'll just put it in at the end of the problem. Anyway, so, okay, so let's apply things. So I said, basically I said, for the n equals 0 term, there is no change to the initial wave function. Now let's consider the n equals 1 term. So for the n equals 1 term, the u that we have is, so I'll call it u sub 1 is 1 over 1 factorial alpha over 2 to the 1 power times d, the second order derivative with respect to space. So I basically get alpha over 2, the second derivative. So now let's take that second derivative and apply it to the wave function. So I have alpha over 2, second derivative, times, or say acting on, the sum, n equals 0, minus 1 to the n power over 2 to the n power n factorial x to the 2n power. Okay, so what's going to happen Well, when I take this derivative, second order derivative, of x to the 2n power, then I basically get the first derivative of 2n x to the 2n minus 1, and I take that derivative and I get 2n times 2n minus 1 x to the 2n minus 2 power. So let me put that inside the summation. So now what we're left with is when u1 is operating on my wave function, then what I have is alpha over 2, the sum, n equals 1. Now, and it's not n equals 0 because n equals 0 was just the constant 1. So this one now is starting at n equal 1, minus 1 to the n power, 2n times 2n minus 1 times x to the 2n minus 2 power divided by 2 to the n factorial. Okay. And now if I think about it, I could actually change this around, because 2n times 2n minus 1 is the same thing as taking 2 to the n factorial divided by 2n minus 2 factorial. So that's pretty good. So now I've got more factorial terms in the problem. So I get alpha over 2, the sum of n to infinity. Again, the n equals 0 term dropped out with the derivative. Minus 1 to the n power, 2n quantity factorial, x 2 to the n minus 2 power divided by 2 to the n factorial 2 to the n minus 2 factorial. Okay, so now what I want to do is I want to clean this up a little bit, because what I have is this ratio of 2n quantity factorial divided by n factorial. And if I work out a few of the terms, I get 2n minus 1, 2n minus 2, dot, 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 all the way down to 2, all the way down to 1, divided by n minus 1, n minus 2, dot, 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 2, and 1. So if I think about it, I can clean this up a little bit by basically factoring out a bunch of 2's. So actually I would factor out n of them. So I take the 2's out of, not this term, I take the 2's out of basically the even terms right here. I factor that out, and I get n of them times n minus 1, n minus 2, dot, 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 all the way down to 1. And what I'm left with now are the odd terms. 2 to the n minus 1, dot, 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 down to 1. And that's divided by n factorial. That didn't change much in the denominator. But now what I have is 2 to the n power n factorial, and then this weird term of all the odd factorials. So the odd terms in a factorial. divided by n factorial. Okay, so that basically cancels out the n factorial, and what I'm left with is 2 to the n power times 2 to the n minus 1. Looks like kind of like a double factorial. And where this double factorial is basically those as a product of all the odd terms. 2n minus 1, 2n minus 3, dot, 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 down to, 3, and then 1. So I've simplified this where I was. I simplified the 2n factorial divided by n factorial into 2 to the n power times the double factorial right here. Okay, so let me put that back into the equation. So that means that the propagator for the first term pi is alpha over 2 times the sum n equals 1 of minus 1 to the n power 2n minus 1 double factorial x 2 to the n minus 2 divided by 2 to the 2n minus 2 factorial. So one thing I didn't really mention was the fact that there is a 2 to the power n when I condense those factorial terms, and that's what got rid of that's what got rid of the 2 to the n in the denominator. So I can pull this 2 inside, and I reduce it even further as alpha times the sum n equals 1 to infinity minus 1 to the n power 2 to n minus 1 double factorial x to the 2n minus 2 power over 2 times 2 to the n minus 2 factorial. Okay, so we've kind of we've reduced it now a little further. Okay, so the next thing to do is to take the u2 term, which will be basically so it's 1 over 2 factorial alpha squared over 2 squared, and then the fourth order derivative with respect to the space. So in the end I get alpha squared, 2 to the 2 is the 4, times 2 factorial will be 8, the fourth order derivative. Okay, so we're going to apply that now to the wave function and see what happens. And we'll do that in the next video.